Welcome to this explainer. Have you ever actually stopped to think about the invisible, honestly brilliant architecture that keeps our critical infrastructure safe every single day? Well, today we're unpacking something truly fascinating, the design of fail-safe hardware.
So, let's start with a really crucial question. What happens when critical railway hardware breaks? We rely on these massive networks of steel and electricity every single day, right? But here's a hard, unavoidable truth. Physical wear and environmental stress mean that random hardware failures are absolutely inevitable. No machine lives forever. Wires are going to snap, metals fatigue, and power supplies drop. Since we literally cannot stop the forces of nature and entropy from breaking things, we have to engineer exactly how they break.
And that brings us to the core concept of our discussion today, the fail-safe principle. This is a design property ensuring that under failure conditions, equipment automatically adopts a state that provides safety for traffic. Basically, since we can't completely stop the wear and tear, systems have to default to a restrictive, safe state the split second something goes wrong. If a train signal breaks, it shouldn't just go dark or, worse, accidentally show a green light. It must immediately show red to stop all approaching trains.
Here's our roadmap for this explainer. We'll briefly look at the inevitability of failure, then explore three completely ingenious engineering solutions: inherent, composite, and reactive fail-safety. And finally, we'll see how they all come together to build a safe system.
All right, Section 1, the inevitability of failure, dealing with physical wear and stress.
It's so vital to set our baseline here. Absolutely no mechanical or electrical component is immortal. Think about it. You've got thousands of tons of steel slamming over these tracks daily. Components face constant physical wear. And environmental stress? Things like pouring rain, massive temperature swings, heavy vibrations, they relentlessly degrade materials over time. Because these random failures simply cannot be prevented entirely, the ultimate engineering solution is to control the failure mode itself. Human lives depend on controlling the consequences of a random equipment failure. If it breaks, it absolutely must fail safely.
Moving on to Section 2, inherent fail-safety, predictable and physical.
Okay, let's dive into this. Inherent fail-safety is our first primary technique. This is where systems are built using components that have very well-defined, highly predictable failure modes. Look at this classic railway semaphore signal. Notice that large counterbalance weight attached to the mechanism, right? If the physical operating wire controlling this signal suddenly snaps, and eventually it might, what happens? Well, gravity just takes over. That heavy counterbalance weight simply pulls the signal arm right back into the horizontal, stop or danger position. The physical laws of the universe basically guarantee the safe state.
Now let's transition from mechanical safety over to electrical inherent safety. What you're looking at here is the classical vital signaling relay, showing its intricate internal contacts and that restoring spring. This relatively small, brilliantly engineered device is essentially the beating heart of classical electrical signaling safety.
What's truly fascinating is just how many specific fail-safe properties are packed into this one single device. First off, the circuitry is designed so that the relay must be actively energized with electricity to show a proceed signal. If the power fails or a wire snaps, gravity and spring pressure physically force the contacts to drop and release, immediately showing a restrictive signal. Furthermore, and this is so clever, to prevent the contacts from melting together and getting stuck in a dangerous proceed state during, say, an electrical surge, they use silver-impregnated carbon contacts. They simply cannot weld. Finally, a little non-magnetic stud prevents any residual magnetism from holding the contacts closed once the power is cut. It is literally a masterpiece of utilizing physics and material science to inherently prevent a dangerous outcome.
Section 3, Composite Fail-Safety, Agreement and Independence.
So, while inherent physical safety is fantastic, it's incredibly hard to achieve in modern, complex electronic microprocessors. A computer chip has millions of microscopic components with a huge variety of totally unpredictable failure modes. So, engineers use composite fail-safety. Here, each safety-related function is performed by at least two independent items. A safe output is only produced if both items agree. Independence is the absolute crucial concept here. It ensures that a single common cause failure doesn't just take down the entire system at once. And this brilliantly illustrates the concept. You've got this logic gate diagram. You have function A and function B working totally independently. If they perfectly agree, great, the system proceeds. But tracking the timeline below, the exact moment of first fault occurs in function A, the fault detection triggers.
Because there's no longer an agreement with function B, the output is instantly negated. The system immediately adopts a safe state. A non-restrictive activity can only progress if the necessary independent channels completely agree that everything is functioning correctly.
Section 4. Reactive Fail-Safety, Rapid Detection and Response.
So how exactly does reactive fail-safety differ from what we just looked at? Well, composite safety requires multiple independent items to agree before an action is taken. It relies heavily on constant redundancy. Reactive safety, on the other hand, operates a bit differently. A single item performs the function, but its safe operation is guaranteed by a secondary item that constantly monitors it to rapidly detect and negate any hazardous fault. It's all about lightning-fast reaction rather than upfront agreement.
Notice the detection plus negation time on this timeline marked here with the letter T. In this specific setup, a hazardous output might actually slip through for just a fraction of a second when a fault occurs. Therefore, T has to be incredibly short. The secondary monitor has to detect the failure and kill the output before that super brief unsafe window can cause any real physical harm to a moving train.
Let's ground this abstract reactive concept in a very real-world example, railway lamp proving. Step 1. A single signal bulb blows out, a totally normal, unpredictable, everyday failure. Step 2. A secondary lamp proving circuit rapidly detects the loss of electrical current from that blown bulb. Step 3. The system immediately reacts and restricts the preceding signal to a safe aspect, like a red light or a caution yellow. This incredibly rapid detection prevents a train driver from speeding into a dark, unlit signal, ensuring absolute safety without needing duplicate bulbs burning simultaneously all the time.
Finally, Section 5, Building a Safe System, bringing it all together.
As we wrap up this explainer, let's just take a quick moment to summarize how these distinct architectural techniques weave together. We know that inevitable hardware wear and environmental stress are absolute constants. To manage this, we use 3 distinct approaches. We have inherent fail-safety, which relies on the predictable, unyielding forces of physical gravity and specialized materials. We have composite fail-safety, which tackles complex electronics by requiring independent, redundant agreement to proceed. And finally, we have reactive fail-safety, which relies on high-speed monitors for rapid hazard negation. Together, these techniques form an impenetrable, layered defense against random failure.
Which brings us to our final thought for today. The next time you ride a train, or honestly interact with any piece of massive, automated infrastructure, take a moment to just look around. Ask yourself, what invisible safety nets are catching the inevitable failures in the technology you rely on every single day? The physical world is constantly wearing down around us, sure, but thanks to brilliant fail-safe engineering, it is specifically designed to catch us when it falls. Thank you so much for joining me for this explainer. Keep learning, stay curious, and I'll see you next time.